Okay, so today we are about to turn to the chapter 4. Uh, mm, so in chapter 4 is mainly about the minimum and maximum problem. So what are those? Well, if you were to ask me, so what is the most important questions that can be asked in calculus? Then, well, I would say that is a minimum and maximum problem, optimization problem. So for given any conditions, and well, you have some real value function, and that function may depend on the several variables. So I mean, so you are working on some multivariable real value function, and you're gonna find the minimum and maximum of the function. So how well for the single variable calculus, then the question is very easy. Well, in the case when your function is differentiable, then you can find the minimum or the maximum of the function by taking derivative, right? So I mean, therefore, a function given a function, you take a derivative and you find all such points that makes your derivative equals to 0, and on such point, and you evaluate the second derivative, and if the second derivative at the critical point is positive, then that means that point is the local minimum. And if the second derivative of the critical point is the negative, then that means your function attains a local maximum of the point. And we're about to do the same thing for two variable and even the multivariable functions. Higher derivative of functions of several variables. Okay. The first, I want to introduce the definition of the n times continuously differentiable functions. Which is this. Well, we say, suppose that you have some real value function defined on Rk. Yeah, so this is a function for Rk to R. So this is K variable function, real value function. And we say this guy is n times continuously differentiable. And this means, well, just imagine all partial derivatives, so K many times partial derivatives. So, and if all these mixed partial derivatives up to order n, if they are all continuous, then, well, we say that my function f is n times continuously differentiable. Okay, so which is easy. So, so therefore, in order to tell if any given function is continuous n times continuously differentiable or not, then you just try to consider the k times k as a n partial derivatives and make sure that all these functions are continuous. Then you're done. Okay. On top of that, we have another theorem that looks like this. Okay, so, by the way, the Cn function means is the collection of all such functions. The collection of all n times continuously differentiable function is, shortly speaking, so we say that it's a Cn function. Okay, so f is a n times many continuously differential functions defined on the k-dimensional spaces, k-dimensional space. And the idea of this statement is this. So I hope you remember. So the mixed partial derivative. So, well, in the case of the two variable functions, fxy was same as fy. So that means, so if you take a partial derivative of a function, x first and y later is the same as y first and x later. So the order of the partial derivation doesn't matter. So what really matters is the number of variables that occurs in the partial derivative. So they are the order things. Okay, and this theorem is true for the n times many continuously differential functions. Okay, so from now on, so without, okay, if I do not specify any further, then you're supposed to consider that all the functions that appears in today's lecture is automatically going to be the Cn function. So therefore, at least for this chapter, you don't need to worry about the order of the partial derivation. Okay. All right. So these are the basic terminologies. Now we are about to turn to the next section. So section 4.2, the extrema of functions of two variables. Oh, by the way, do you know the meaning of the extrema? Extrema means minimum or the maximum. So minimum or maximum, they are sometimes for the extrema. So, well, so therefore, if I say extreme value theorem, do you remember the extreme value theorem? So that means that theorem guarantees the existence of the minimum and the maximum of any given function defined and closed and bounded. Okay. So extrema means the plural of the extremum. So this section, so therefore, in this section, we are about to discuss the minimum or the maximum of two variable functions. Yeah, right. Oh, later on, we are going to discuss the minimum or maximum, the minimum and the maximum of multivariable functions, but that theory is going to be too much complicated for now. So yeah, please allow me to discuss only two variable functions. First, maybe in my next lecture, yeah, I'll have opportunity to discuss the extrema of the multivariable functions. But anyway, for now, so minimum and maximum for two variable functions. Okay, good. Okay. Well, just as we did in the freshman calculus, we still have the definition of the local maximum and the local minimum. Okay. What are these? So we say f, well, we have the multivariable real value function f, and we say f as a local minimum, f of a at a point A indeed. Well, if you can find any subordinate open ball around centered at A, and on this neighborhood, on this open ball, if this inequality is true, so what is this? That means in this open ball, at least in this open ball, the function value of A, a function value of f at A is the minimum on this open ball, right? If you can find such an open ball around point A, then we say f is a local minimum. And same is true for the local maximum. The function value f of a is called to be the local maximum. if you can find an open ball around the point A, and on this open ball, if f of A is the maximum function value on this open ball, then you say, aha, f of A is the local maximum of the function. So this is the local maximum and local minimum. So local minimum and local maximum, sometimes we just call them local extremum of a function. And we say the local maximum or local minimum is strict if this inequality is strict inequality, except for x equals to a. Okay, so okay, good. So some couple of examples. All right, so remember that any two variable real value function is best described by drawing a graph of the function on the three-dimensional plane. So let us say these are the graphs of the two variable function f. And local maximum, it typically looks like this. So on this, well, this is the open neighborhood. This is the point A. This is the open neighborhood. And on this open neighborhood, this point is the maximum. Therefore, this guy is the local maximum. And likewise, at least locally, the graph near the local minimum looks like this. And well, as you can see from this picture, these local maximum and these local maximum and minimums, they are all strict local extremums, right? Because, well, other than this point, or the inequality, the function values are all less than or equals to this point. And likewise, except for this, besides this point, all these function values are strictly greater than this point. Okay, so these are local minimum and local maximums. What about this? This is, well, this graph looks like this. Something looks like a parabola, but with the parallel translated. What do you think about this one? Is it local minimum? Yeah, this is a local minimum. But this is a local minimum. This is not strict local minimum. Why? Because on this open neighborhood, no matter how small your open neighborhood is, but you can still find another point whose function value is the same as this one. Okay, good. So, okay, from now on, so we're gonna discuss how do we identify these local maximums or local minimums. The first idea is the first derivative test. Okay. Okay. So before I introduce the first derivative test, so let us compare the theory from the freshman calculus. So when we were working on the single variable functions, how did we find the local extremum? Well, first you are supposed to find all the points that makes the derivative equal to 0, right? And all these points are called to be the critical points. And same is true for the multivariable function. In order to find the local maximum or local minimum, then first thing that you're supposed to do is you're supposed to find the point that makes your derivative equals to 0. And hey, but what is the derivative of this multivariable function? These two variable functions. F is a function from R to R, right? So we are talking about this function. And the derivative of this function is a matrix that has the one row and two columns, which is fx and fy. So this is the derivative, right? Right? Yeah. So therefore, and we can identify this guy as the gradient vector. You know what? I hope you remember the definition of the gradient vector field. The gradient vector field is a vector field whose components are exactly these partial derivatives. So, therefore, for our case, the critical point must be the point that makes your gradient vector equals to 0. I am pretty sure that these points must be called as the critical point. And actually, that is very true because of the next theorem. Okay, so, well, we have the differential function, well, this time from Rn to R. So this is n variable function. And suppose that f has a local extremum at the point A. Then the partial derivative of f are all 0. So in other words, if your function f attains the local extremum at the point A, then this means the gradient vector field, the gradient vector at this point must be 0, right? And this point, I want to call this point as a critical point. Okay, so let me try to prove this. Okay, so because of our hypothesis, so we are assuming that f has a local extremum at point A. Then what you're gonna do is I wanna define a single variable function like this, depending on the value of t. So what is this? So I compose this function with another curve. So, well, this guy is only depending on the parameter t, and this is a curve, and this curve is now again composed with another real values function. So this is a single variable function, so which takes one number as an input, and we're gonna give you another a number as an output. So this is a single variable function, or just like we did in the freshman calculus. Oh, wait. So I want to. I really like to explain about this curve. So what is this curve? This is actually a straight line. At when t equals to 0, this curve is passing through the point A, and as t increases, and E of I means the standard unit vector in the direction of I. So in other words, this is a vector. So all the component of this vector equals to 0. But when the i's component is 1, so this is the critical, this is the standard unit vector. So in other words, this guy is a what? So this is a straight line which is parallel to the xi axis and passing through the point A, right? Well, like this. So this is the point A, and this is a straight line which is moving parallel to the direction of line. So we are composing this curve with the function. Okay, so in this picture, so this curve, well, this is the graph of the, well, here in this picture, we are assuming that f is a two-variable function, and this is the graph of the two-variable function. And well, if I compose then there must be a corresponding values, right? On this graph. And and since we are assuming that this point is the local extremum, therefore the graph of this guy, the graph of the image of this curve must be looks like this. So which has the apex at precisely like this. And what do you think is the rate of change at this? Which equals must be zero, right? So, So when t equals to 0, so I mean when you're at this point, the rate of change must be 0. But you know how to deal with this derivative. So this is the composition of the multivariable functions with multivariable real value function with another curve. So therefore its derivative is the gradient of f dot product with the velocity vector. But you know the velocity vector of this guy is the EI. And also don't forget to plug in t equals to 0. So you plug in t equals to 0. So this is now f of gradient of f of a dot EI. So what is this? So the i's component of this guy is, which is this. So we have this one, and this guy equals to 0. And since this equality is true for all n's from 1 to n, therefore the gradient vector at a must be the 0 vector. Okay. So this gives us the idea how to identify the local extremums of the multivariable. So that is, once a function is given, then you try to find all these points that make your gradient vector equal to 0. And these points must be the candidate for the local extremum of your function. Okay. All right. Let us try to find the local extremum of this guy. So x squared plus y squared. So due to the theorem 4.2, the local extremum can only appear on the critical point. Therefore, so this is the gradient vector of the function, and I am looking for the point that makes my gradient equals to 0, right? And what is this? The only solution of this back equation must be x equals to 0 and y equals to 0, right? So that means, so the origin, 0, 0, should be the only candidate of the local extremum of function. And what do you think? Is it local maximum or local minimum? I am pretty sure that this one must be local minimum. Why? Because so if you try to draw the graph of the function, then this would look like this. Okay. And since we are talking about so this is the graph, and at the origin, this is obviously local minimum. So we were able to find this. Okay, so this is a local minimum. Okay. Okay, now I want to challenge you with this question. Suppose that you are able to find a point that makes your gradient vector equal to 0. Then, is that point always attain a local maximum or minimum of your function? The answer is no, not necessary. Most times, the critical point, on this critical point, your function attains the local minimum, but sometimes, so the some critical point fails to attain either local maximum nor local minimum. The example is this. Well, this is very easy function. Well, so even though this looks like a two-variable function, but yeah, one-variable function, but say that this is two-variable function and independent from choice of. And well, here I am trying to find the critical point. Well, this is a gradient vector, and for which x and y this gradient vector is equal to 0. Well, obviously, on all such points, my gradient vector equals 0, right? Okay, so, but on these critical points, my function fails to be local maximum nor local minimum. Why? So the best explanation is given by drawing the graph of this. This is the x coordinate, this x-axis and y-axis and z-axis. So, and if you try to draw the graph of this guy in three-dimensional Euclidean space, the graph of the function will look like this. Okay, and basically, all those points on this x-axis must be the critical point of the function. Okay, but okay. So for instance, let me try to consider this origin, this point, the origin. Well, even though the origin is the critical point of this function, but however, okay, just try to take a small neighborhood of this origin. But no matter how small your neighborhood of the origin is, but you can still find a point whose function value at the point is greater than the origin, and you can still find, at the same time, you can still find another point in the neighborhood, and on that point, the function value is strictly less than the function value at the origin, right? So this is neither local maximum nor local minimum. Yeah. So the origin is, even though the origin is the critical point, but that is not the local maximum nor local minimum. Yeah. So this means finding the local maximum or the finding the problem of the finding local maximum and local minimum is way more complicated than you think. So even though you are able to locate all these critical points of your function, but are they real local extremes? Then that will require another piece of analysis. Okay. All right. What analysis? So that is what you're going to discuss from now. 그러니까 로컬 맥시멈과 로컬 미니멈을 찾는 문제가 상당히 이제 골치가 아프다. 우리가 원배리어 펑션의 경우에는 그래프를 그리고 대충 이제 문법으로 이제 로컬 맥시멈, 로컬 미니멈. 근데 이제 투배리어 펑션에 대해서는 이제 그래핑 캘큘레이터가 없다라고 가정합니다. 그 포인트, 크리티컬 포인트에서 로컬 맥시멈, 로컬 미니멈을 우리가 확인하는 것이 생각보다 엄청나게 어려웠어요. 그러니까 투배리얼 펑션은 그나마 우리가 그래핑 캘큘레이터 그리는 거 알 수가 있는데, 쓰리배리얼 펑션부터는 그래프를 그리는 것조차 불가능해요. 그럼 그 주어진 크리티컬 포인트가 로컬 맥스인 로컬 미니멈이고, 그러니까 다변수 함수 이론에서는 로컬 맥스와 로컬 되게 어려워요. 되게 중요한 문제라서 이 문제에 대해서 오늘 한번 집중적으로 아마 오늘 다음 시간까지 한번 집중적으로 합니다. Okay, the symmetric matrix. Well, this is suppose that A is a square matrix. Yeah, because it's n by n matrix. And we say this matrix is a symmetric matrix. The symmetric if Aij is the same as Abi. So what does it mean? So that means, well, about this diagonal entries, about these diagonal entries, these component, the entries of the matrix, they are symmetrical, right? This number must be the same as this number. So if your matrix looks like this, then we say the matrix. The theories on the symmetric matrix is very deep, especially so in particular. So if you register yourself to the applied linear algebra course, then an entire chapter is purely dedicated towards the theory on the symmetric matrix. So, and we cannot cover them all, but we're going to study just a couple of things about the theories on the symmetric matrix. Okay. And the most important symmetric matrix that we'll be discussing is the Hessian matrix of function f. All right. Okay. So what is the Hessian? I have a function f. Sorry. I have a function f from Rn to R. Then for any given n, we say, okay, suppose that this function is C2 function, so twice continuously differential functions. And the Hessian matrix of this function is defined like this. This is n by n matrix. So I mean, the size of the row and the columns is the same as the number of the dimension of the domain. So what f taking derivative to the first variable and another the first variable, and first variable, second variable, the first and variable, second variable, first variable, second variable, second variable. It all goes like order. Can you recognize that this is a symmetric matrix? Yeah, absolutely. Because well, this is C2 function, therefore the order of the partial derivation doesn't matter. So, well, for instance, fx1 and x2 is the same as fx2 and x1, right? And also this guy is the same as this one, and this guy is the same as this one. So Hessian matrix is always a symmetric matrix. But to be precise, so this is a not matrix of numbers. This is matrix of functions. But if you plug in, evaluate all these functions at some fixed point, then this Hessian matrix is going to be a symmetric matrix of numbers. I mean, so Hessian matrix is a symmetric matrix. Okay, but however, so dealing with this n by n Hessian matrix will be too complicated for today's lecture. And I told you so that today we're mainly discussing the case when n equals to 2 variable functions. So from now on, we're going to consider the 2 by 2 Hessian matrix. And 2 by 2 Hessian matrix is 2 by 2 symmetric matrix. And so before we start to study the Hessian matrix, and please allow me to introduce some basic theories on 2 by 2 symmetric matrix. Okay. Yeah, I am running out of space. Suppose that we have the 2 by 2 symmetric matrix S. So it has 3 numbers, P, because this is 2 by symmetric matrix, so this number must be the same as this number. So P, Q, Q, R. So typical 2 by 2 symmetric matrix will look like this. And for this given symmetric matrix, and we say this symmetric matrix is positive definite. So what is the definition? Is given by this. For any given 2 by 2 matrix, we can associate a quadratic polynomial like this. Is it quadratic polynomial? Yes, this is a quadratic polynomial because of this reason. So SUV will defined to be a 2 by 2. Well, U is always assumed to be two vector, two-dimensional vector. So U dot SU can be written, well, in terms of the matrices, can be written like this. This is U, and this is S, and this is U, right? S times U is this. Okay, so if we multiply this matrix and that column vector first, then this is going to be P times U plus Q times V, and Q times U and R times V. And again, multiplying by this guy with this is basically we're taking the dot product. So U times this whole thing plus V times this whole thing. So P U squared Q times UV and Q times VU and R times V squared. So simplifying that, so we have this looking polynomial. This is what? This is degree 2 polynomial. So this is quadratic polynomial. So therefore, for any given symmetric matrix, we can associate a quadratic polynomial U dot SU in this manner. And what is the definition of the positive definite matrix? And in order S to be positive definite matrix, then this polynomial must be always positive for all non-zero vector U, right? I mean, so if vector U is a zero vector, then this number, then this function equals to 0, which is no-brainer. But if this polynomial is always strictly positive for all non-zero vector U, then in that case, we say the matrix S is positive definite. Okay. All right. Hey, what is negative definite? And we also say the symmetric matrix S is negative definite if minus of S is positive definite. Hey, what is this? This is very weird definition. Yeah, this is a correct definition, but this definition requires a little bit explanation. Well, in order S to be negative definite, then the associated quadratic polynomial, if this guy, in other words, if this guy is always strictly negative for all non-zero vector U, then we say the matrix S is negative. That is the meaning of the minus S is positive. So, I mean, if this polynomial is always strictly negative for all non-zero vector U, so this is negative definite. And finally, indefinite. Well, S is a symmetric 2 by 2 matrix is indefinite if U dot SU, if this quadratic polynomial attains both positive and negative values. Okay. Okay. Good. All right. And there is very useful equivalent criteria of being positive definite. We have a 2 by 2 symmetric matrix S. And suppose that we still do not know that this guy is either positive definite. But it says S is positive definite if and only if, so this is the both two-sided implications. If and only if there is a positive number m such that satisfies this inequality. If you can find such a positive number m that satisfies this inequality, then that is equivalent to say S is positive definite. Okay, is it? Yeah. So so m is a positive number. So that means, well, if you have such an inequality, then for all non-zero number u and v, for all non-zero vector u comma v, then this is always positive if this vector is non-zero, right? And if this guy is positive, then this quadratic polynomial is also positive. Therefore, that implies this associated quadratic polynomial is always positive for non-zero vector u. So that implies S is positive definite. Okay. Okay. So this side of this implication is very easy. Okay. Great. Okay, so if you have such a positive number m satisfying this inequality, then it will be really easy to show that S is positive. Okay, so the proof is omitted. Okay, so let us talk about the other side of implications. Now, suppose that S is positive definite. Then we want to talk about this associated quadratic polynomial, which is p times u squared, 2 times uv plus r times v squared. So this is polynomial. So therefore, this must be always continuous for entire plane r squared, r2. Yeah. So yeah, because this is polynomial, which is obvious. And if your function is continuous, then restricting the domain, the function is still going to be continuous. So therefore, since this guy is continuous for this entire domain, therefore, now I want to restrict our domain into this unit circle, which is a closed and bounded. So therefore, as is the same function on this unit circle also must be continuous. And you have to remember, for any continuous function defined on the closed and bounded set, that function must attain the log maximum and the minimum at some point. Okay, so therefore, this function must attain the minimum value on this unit circle at some point. I will say the point is equal. And let me say the function value of S at this point is m. And I am pretty sure that this number must be positive. Why? Because S is positive, right? And this guy is obviously non-zero vector because this is unit vector. Unit vector cannot be zero. So, and since we are assuming that the S is positive definite, if you plug in this vector into this quadratic function, but our function S was positive definite, therefore this number must be positive. Okay, good. Okay. Now now out of this unit circle, so for any general vector, so now this time this vector may not be a unit vector, but any such a vector can be written as unit vector times some scalar multiple, right? So basically, A must be the length of this vector, and z comma u gives z comma w is going to be the normalization of this vector, and this normalized vector is a vector that lies in the unit circle C. So we can always write this vector as a times such a vector, such a unit vector. So S u comma v can be written as S of az comma aw, and well, because of definition of this associated quadratic polynomial, so this is p times this guy squared plus 2 times q times the first component times second component plus r times the last component squared. So this is the quadratic polynomial. And simplifying and factoring out the common factor, so a squared has been factored out. So p z squared times 2, so we have something like this. And what is this? This guy can be also interpreted as, say, if this guy is the same as a squared carries over, but this expression between the parentheses can be written as S of z comma w, right? So this is precisely this one, right? So this is the function value of s at z comma w. And z comma w is a unit vector, right? And the function value of this guy on this unit circle is always greater than equals to m, right? Because of this. And so this number is the minimum of the function on this unit circle. So this guy is always greater than equals to the m. Okay. So and z squared plus w squared, this guy, since this guy is unit circle, so z squared plus w squared is 1. So this one is the same as this. Okay, because you can always multiply something by 1, but that doesn't change. And and can be said, oh, not m squared. So, messed up. This is m times a squared, az squared plus aw squared, and but az is u and aw is v, right? Because of this. So this is m times u squared plus w squared, v squared. So the function value of s at any such a vector is greater than equals to some positive number times u squared plus v squared. So we're done. So, okay, so good. Okay, what's next? Okay, so this theorem sounds a little bit complicated, but okay, so before we even try to prove this, okay, let us try to understand the theorem. So if you can understand the theorem, you're kind of 90%. Suppose we have some 2x2 symmetric matrix S. And we are also assuming that S is positive definite. Then because of the previous theorem, then you must be able to find a positive number m, and this m must satisfy this inequality for all such u and right? Because S being positive definite is equivalent to the existence of such a number, real number, positive real number. So you can always find such a number m. Okay, so S is a positive definite matrix. Then now we have another symmetric matrix T. And we do not know this, so we do not know T is either positive definite or not. But suppose that the entries of the symmetric matrix are small enough. Then S plus T is still positive definite. And S plus T, comma UV is greater than or equals to M over 2 times U squared plus V squared. Okay, so basically this means we have suppose that a 2 by 2 symmetric matrix S is positive. Then if we perturb entries of the symmetric, if we perturb the entries of S by just a little bit, but still maintaining the symmetricity, then the resulting matrix is still going to be the positive. 그러니까 이런 거죠. 그러니까 우리가 2x2 시메트릭 매트릭스 3개 살고 있는데 여기서 어떤 매트릭스 딱 뽑았는데 되면 파지티브 매트릭스. 그러면은 그 시메트릭 매트릭스 3개에서도 S를 살짝 엔트리들을 이제 흔들면은 살짝 시메트리시티를 유지하면서 매트릭스 S가 변할 수가 있죠. S의 엔트리들이 변할 수가 있겠죠. 근데 그게 우리가 그 엔트리들을 너무 심하게만 바꾸지 않으면은 파지티브 데피니트라는 성질이 계속 유지가 됩니다. 그러니까 파지티브 데피니트는 살짝 리틀 퍼터베이션에는 우리가 그 성질을 잃어버립니다. 살짝만. 오케이. Okay. So right, T is A, B, B, and C. Then the associated quadratic polynomial for the symmetric matrix T must be this, which is A times U squared. And oh, sorry, I messed up. And 2. Yeah, I missed. I forgot 2. Yeah, 2 times B times UV plus C times V squared. So this is the associated quadratic polynomial for symmetric matrix. And I want to show that if the entries of T are small enough, then this associated quadratic polynomial for T is bounded below by minus M over 2 times U squared plus V squared. Hey, what is this M? This M is coming from the matrix S. I'm going to show this inequality is true for small A, B, and C. Okay. Good. So I am running out of space. Yeah. I want to divide into 2 cases. Well, the first case is B's non-negative number, and the second case is B's negative number. Suppose that this number B is non-negative, then U plus B squared is this, and this is always non-negative, right? Because this is perfect square. And so if you multiply, and sending this guy and this guy to the other side of this inequality, and if you multiply by this non-negative number, then we have this inequality, right? Well, because B is non-negative. So this is the associated quadratic polynomial for symmetric matrix T. But this middle guy, the middle term, 2 times B times UV is, well, greater than equals to
b times minus u squared minus b squared. So simplifying this, so this is a minus b u squared plus c minus b v squared. Right? And if b is negative, then this guy is still non-negative, and moving this guy to this side and multiplying the both sides of this inequality by this negative number, then this, when this inequality is now flipped, so we have this inequality, right? And again, this middle guy is greater than equals to this one. So this guy is greater than this guy, right? And again, simplifying this, we have this. So we have these two inequalities, depending on the case, depending on signs of the sign of B. Okay, now what? Now we take the absolute values of A, B, and C. They are all less than m over 4. So I mean the absolute values of A, B, and C, they are smaller. If these, well, if these numbers are less than this guy, then A minus B, well, because of the triangle inequality, this guy is less than absolute value of A plus absolute value of B. But since they are all less than m over 4, so their sum must be also less than m over 2. So then this implies a minus b is greater than equals to negative m over 2. Okay. Well, likewise, well, so c minus b and a minus b, c plus b, they are all can be proved that all these guys are can be easily shown to be greater than equals to minus m over 2. Okay. All right. So this guy, and this guy, all these numbers in this parenthesis, they are all known to be greater than equals to minus m over 2. So this is, under this assumption, this guy is greater than equals to minus m over 2 times u squared plus v squared. And this guy is also greater than equals to minus m over 2 times u squared plus v squared. So for these both cases, so associated quadratic polynomials are they are all greater than equals to minus m over 2 times u squared plus v squared. Okay. Under this assumption. Oh, so we are done. Okay, so we proved this. Okay, so how small? So for sufficiently small a, b, and c, so we have this inequality. And how small? If you all these entries, so all these numbers, the absolute values of all these entries, if they are all less than equals to this guy, then we have this inequality. Okay, now we will talk about S plus T, the positive definiteness of S plus T. S is symmetric and positive definite matrix, and T is just a symmetric matrix. So this is going to be still symmetric matrix, right? And the associated quadratic polynomial of this guy should be this, but this is u dot su plus u dot tu. And because of our assumption, this guy was greater than this guy, right? So this was greater than m times u squared plus b squared. And because of this, this is minus m over 2 times u squared plus b squared. So therefore, their sum is greater than equals to m over 2 times u squared plus b squared. So what does it mean? So we were able to find if this is positive number, and this associated quadratic polynomial of this symmetric matrix is known to be greater than some positive number times u squared plus b squared. And this implies S plus T is still going to be positive then. Okay, good. Okay, so I believe this is the most important theorem in today's lecture. Okay, I have a seat, so f is twice continuously differential function, and f is defined on the open sum open set in R2. So this is two variable function, two variable real value function f. And suppose that this point is a critical point, because at this point your gradient vector equals to. And this is the critical point. And on this critical point, we can try to compute the Hessian matrix of F at this point. You know, you remember the definition of Hessian. And this Hessian matrix is obviously 2 by 2 symmetric matrix, right? And if this guy is positive definite, then F has a strict local minimum at this point. And if this Hessian matrix is negative definite, then F has a strict local maximum at this point. And if this Hessian matrix is indefinite, then F is neither a local maximum or nor local minimum. This point is sometimes called the saddle point, 안장점이라고 해요. 이거 비교해 보세요. 우리가 1학년 1학기 때 배웠던 게 크리티컬 일변 함수가 있는데 크리티컬 포인트가 있어요. 크리티컬 포인트에서 이계도 함수가 양수이면은 로컬 미니멈. 여기서도 그러니까 해시안이 어떻게 보면 이계도 함수의 역할을 하고 해시안이 아닌 이계도 함수가 포지티브 양수이면은 로컬 미니멈. 해시안이 아닌 이계도 함수가 네거티브는 로컬 미니멈. 근데 해시안이 이제 우리 1학년 1학기 때는 이변 함수가 이제 음수도 아니고 양수도 아니고 그런 케이스 없어요. 근데 이제는 그런 경우에는 이렇게 패들 같은 거는 안장점 같은 거는 이변 함수부터 등장하게 됩니다. 이거 한번 증명해 볼게요. 자, 우리가 A만 한번 증명해 볼까요? 해시안이 포지티브 데피니트 하면은 F가 스트릭트 로컬 맥시멈. 자, F가 이게 해시안이 포지티브 데피니트라고 가정을 해볼게요. 그러면은 어떤 C, D란데 요 C, D라는 점에서 요거 CD를 댔을 때 요게 포지티브 데피니트라는 소리잖아요. 그치? 근데 요 fxx, fxy, fyx 요 네 개의 함수들이 전부 다 연속 함수들이지. 그치? 그래서 C, D에서 살짝 벗어난다 하더라도 요 숫자들이 크게 변하지 않을 거 아니에요. 그치? 그러면은 여기 C, D 근처에 있는 모든 포인트들에서도 아까 위에 정리에 의하면은 숫자들이 살짝 바뀌어도 시메트릭하게 바뀌기만 하면은 얘가 여전히 거기 포지티브 데피니트 하다며. 그치? 그러니까 이 얘기는 뭐냐면은 우리가 C, D 근처에 어떤 작은 오픈볼을 하나 잡을 수 있어가지고 이 오픈볼 내에 있는 모든 점 위에서 해시안이 포지티브 데피니트 하게 되는 이런 오픈볼을 잡을 수가 있다는 뜻이에요. 그래서 이 오픈볼 안에서는 여기 C, D고 이 오픈볼 안에서는 해시안이 언제나 포지티브 데피니트. 자, 그러면 우리 여기서 오픈볼 안에 임의의 점을 하나 잡아볼까요? X, Y. 그러면은 이 원점이 오픈볼의 분점이 C, D지 여기서부터 여기까지 벡터를 하나 잡고 6,V를 XY 빼기 C, D. 자, 그러면은 우리가 지금 G라는 함수를 잡았는데 G가 뭐냐면은 이 F라는 거기 함수와 C 플러스 TU, D 플러스 TV가 이게 뭐야 이게? 이거 직선의 거기 방정식이죠, 그쵸? T가 0일 때는 C, D를 지나고 T가 1일 때는 T가 0부터 1까지 변하면 쭉 이 빨간 선상을 따라가다가 T가 1이면은 정확히 이 점에서 딱 멈추게 되는 그런 직선의 방정식이지, 그치? 그쵸? 그러면은 요거는 그러니까 T에만 의존하는 T를 받으면은 어떤 GT라는 숫자를 돌려주는 1학년 1학기 센스에서의 일변함수잖아, 그치? 요거 한번 미분해 볼게요. 근데 요거 미분하는 거 우리 잘 알지? 요거 그레디언트와 거기 요 커브의 빌러시티 벡터와의 내적이잖아, 그치? 커브의 빌러시티 벡터가 뭐지? 상수가 없어지고 1 되고 1 되니까 얘의 빌러시티 벡터는 그냥 6,V가 된다. 되는 거죠. 그치? 그러니까 얘와 얘의 내적인 거죠. 그런데 요거는 우리가 어떻게 생겼는지 알죠? fx, fy죠. 그렇죠? 그래서 u 곱하기 첫 번째 컴포넌트 플러스 v 곱하기 두 번째 컴포넌트 이렇게 되겠죠. 그렇죠? 그다음에 얘 뒤에 이계도 함수 한번 구해볼까요? 그럼 이건 똑같은 작업을 또 하는 거예요. 그럼 이 녀석의 그레디언트 벡터. 이 녀석의 그레디언트 벡터는 뭐야? fxx, fxy로 이루어져 있겠죠. 그렇죠? 근데 얘의 그 빌라스티 벡터는 또 u, v가 되겠지? u는 그대로, 요 u는 그대로 내려오고요. 똑같이 요 v는 이대로 내려오고 얘의 그레디언트 벡터는 이게 될 것이고 얘의 빌라스 벡터는 이게 되겠죠. 그렇죠? 그래서 이게 약간 좀 복잡해지는데 이걸 지지고 볶고 하면은 이런 식의 어떤 함수가 나타나게 돼요. 그렇죠? 자, 그런데 여기서 되게 중요한 게 뭐냐면은 u 제곱 곱하기 요 친구 2uv 곱하기 요 친구 v 제곱 곱하기 요 친구인데 요 친구를 우리가 이렇게 매트릭스를 이용하면 이렇게 바꿔 쓸 수가 있다. 그렇죠? 요거를 볼 수 있는 게 되게 중요해요. 요 녀석이 왜 이렇게 되는 건지 이거가 이해가 되시면 이제 이게 가장 어려운 이 증명이 가장 어려운 부분이에요. 이게 왜 이게 이렇게 되는지 보이세요? 그렇죠? 보이죠? 보여요? 자, 그러면은 이게 가운데 끼어 있는 이 친구가 요 포인트에서의 해시안 매트릭스야. 그렇죠? 자, 그러면은 자, 여기서 갑자기 뜬금없이 테일러의 정리를 한번 이용할게요. 우리가 지금 G란 함수에 1궤도 함수, 2궤도 함수를 구했잖아. 그치? 근데 T란 함수의 G란 함수의 테일러 전개는 2차 테일러 전개는 이렇게 생기겠죠? 이게 세타는 0과 T 사이인 어떤 적당한 포인트고, 그치? 1학년 1학 때 배웠죠? 원점을 중심으로 한 테일러 전개죠? G란 함수에. 그쵸? 근데 T에 1을 대입해봐. T1을 대입하면은 요게 되고, 요게 되고, 요게 되고, 요게 되겠죠. 그쵸? 자, 그런데 요 G 프라임 제로가 얼마야? G 프라임 제로는 여기 제로를 대입하면은 C, D에서의 그레디언트 벡터잖아요. 그치? 근데 우리 여기 요 포인트에서 그레디언트 벡터가 제로 벡터라고 했었지. 그치? 그래서 얘는 빵이야. 그렇죠? 얘는 우리가 없애도 돼요. 그다음에 G0 CD는 뭐야? G0는 뭐지? G가 아까 요거였으니까 제로 대입하면은 F 오브 CD가 되는 거죠. 그렇죠? 그러니까 C, D에서의 함수값이 되는 거고. 그렇죠? G 오브 1은 얼마야? G 오브 1은 얼마냐면은 G가 1이 되면은 C 플러스 U, D 플러스 V가 되지. 그 C 플러스 U, D 플러스 V니까 X, Y잖아. 그치? T가 1이면. 그쵸? 그래서 G 오브 1은 F 오브 XY. 얘는 빵이고. 근데 아까 이게 G 더블 프라임이 아까 뭐라고 했었지? G 더블 프라임이 이 해시안이 가운데 들어가는 어소시에이티드 쿼드레이크 폴리nomial. 그러니까 이 녀석을 2분의 1 곱하기 UV 해시안 UV로 쓸 수가 있겠죠. 그치? 자, 그런데 이게 C 플러스 세타 U, D 플러스 세타 V에서의 헤시안 매트릭스가 가운데 껴있죠. 그렇죠? 근데 우리가 요 영역 내에서는 모든 헤시안 매트릭스가 다 이제 퍼지티브 데피니타 되는 그치? 근데 세타가 0과 1 사이의 값이니까 사실 여기 이 선과 이 선분 중간 가운데 어중간한 요 점에서의 헤시안을 계산하는 소리거든. 그쵸? 자, 세타가 0과 1 사이에 있는 숫자라며. 근데 요 포인트에서 헤시안은 당연히 포지티브 데피니타겠죠. 그래서 요게 포지티브 데피니트. 여러분들 포지티브 데피니트 하면은 요 값은 언제나 0보다 같거나 크겠죠. 그렇죠? 이게 포지티브 데피니트 정의잖아요. 그렇죠? 그래서 예칭 이것보다는 그래서 요 릴레이션을 다시 쓰면 이렇게 되는데 요것보다는 요게 언제나 같거나 작게 돼 있어요. 그리고 이때 이게 이퀄리티가 되는 유일한 경우가 뭐지? 이퀄리티가 되는 유일한 경우는 UV가 제로일 때. 즉 여기 C, D일 때만 요 이퀄리티가 X, Y가 C, D일 때만 성립하게 됩니다. 다시 말하면은 이게 뭐냐면 요 오픈볼 안에서의 모든 XY에서의 함수값은 C, D에서의 함수값보다 같거나 크게 됩니다. 그리고 요 이니퀄리티는 제 스트릭트한 이니퀄리티. 그래서 이걸 증명할 수가 있어요. 비슷하게 이것도 증명할 수가 있어요. 네거티브 데피니트도 증명할 수 있고요. 이것도 증명할 수 있어요. 시간이 또 많이 없네. 자, 우리 요거 한번 볼까요? 자, C, D에서 크리티컬 포인트인데 어떤 C, D의 그 크리티컬 포인트 근처에 우리가 어떠한 네이버후드를 잡든지 간에 U가 아무리 작아도 상관없어요. 어떤 모든 네이버후드에서 다음과 같은 상황을 벌어진다고 합시다. U 내부에 있는 어떤 점이 있어가지고 요 점에서의 함수값이 요 점보다 함수값보다 크고 요 점에서의 함수값은 요 점에서의 함수값보다 이렇게 작고 이런 현상이 발생하는 것을 우리가 안장점이라고 불러요. 그러니까 이런 포인트를 말하는 거죠. 그치? 그래프가 이렇게 생겼을 때. 그러니까 여기에서 요 포인트 근처에서는 요 포인트 근처에 아무리 작은 네이버후드를 잡아도 이 함수값보다 높은 함수값을 갖고 있는 점이 존재하고 이 함수값보다 낮은 함수값을 갖고 있는 점이 존재하죠. 그치? 이런 점이 바로 안장점이라는 거죠. 그러니까 바로 이렇게 요 C번 경우에 해당되는 거죠. 그렇죠? 자, 그러면은 우리가 여기서 중요한 걸 배웠는데 그래서 세컨드 데리버티브 테스트를 배웠어요. 그래서 자 그러면은 이제 우리가 어떤 크리티컬 포인트가 로컬 맥시멈인지 로컬 미니멈인지 파악하기 위해서는 해시안을 우리가 보면 해시안의 파지티브 데피니스를 보면 되겠구나, 그렇지? 그러니까 요 녀석이 그러니까 여기 결국 C, D에서 어떤 숫자가 나올 테니까 어떤 주어진 2x2 매트릭스가 2x2 시메트릭 매트릭스가 파지티브 데피니스인지 아닌지 확인만 하면 끝나는 거죠. 그런데 우리가 어떻게 확인을 해야 되지? 거기에 대해서 얘기 안 했고요. 거기에 대해서 마지막으로 얘기해 드릴게요. 음, 음. 이건 그렇게 어려운 정리는 아닌데요. 어떤 주어진 2x2 시메트릭 매트릭스가 있을 때 이 녀석이 파지티브 데피니트가 되기 위한 조건은 뭐냐면은 첫 번째 요 P가 양수이고 PR 빼기 Q 제곱. 다시 말하면 요 매트릭스의 거기 행렬식이죠. 디터미넌트죠. 첫 번째 엔트리가 양수고 요 전체 이 녀석의 행렬식이 양수이면은 이게 파지티브 데피니트예요. 그 다음에 네거티브 데피니트 하기 위해서는 P가 음수이고 행렬식은 또 양수야. 그러면 이게 S가 네거티브 데피니트 되는 거고요. 행렬식 자체가 음수가 돼버리면은 이 녀석은 인데피니트. 그러니까 이 경우에는 새들 포인트가 되는 거죠. 그렇죠? 인데피니트하다는 거는 이제 양수되고 음수된다는 소리니까. 이거 증명은 여기 있는데요. 그렇게 크게 어려운 증명은 아니니까 여러분들이 읽어보시면 되겠습니다. 리딩 어사이먼트도 아닐게요. 미안해요. 제가 진도가 약간 늦어져 있어서. 그러면은 오늘 남은 시간 제가 2분이 남았는데 문제만 얼른 잽싸게 풀어보고 자, 잽싸게 풀어볼까요? 자, 요 함수의 크리티컬 포인트를 모두 찾고 가까이 크리티컬 포인트가 로컬 맥시인지 로컬 미니멈인지 새들인지 확인해 보라는 소리예요. 자, 크리티컬 포인트 찾는 거 쉽죠? 그쵸? 그레디언트 벡터 구한 다음에 그레디언트 벡터가 제로가 되는 포인트가 뭐야? x가 마이너스 1이고 y가 0일 때죠. 그런데 이 녀석의 해시한 뭐죠? 이 fxx는 이게 fx니까 fxx는 이 녀석 x에 대해서 미분한 거죠. 그럼 2죠. fxy는 뭐야? 이 녀석을 y에 대해서 미분하니까 0이지, 그치? fyx도 역시 0이 되겠죠? 이 녀석은 뭐야? fy를 y에 대해서 미분한 거니까 이 녀석을 y에 대해서 미분하는 거죠. 근데 이 녀석은 이게 양수고 이게 행렬식이 얼마야? 4지. 그러니까 이 녀석은 파지티브 데피니션. 그러니까 이 얘기는 요 포인트는 로컬 미니멈이다. 쉽죠? 되게 쉽죠? 자, x제곱 마이너스 y제곱 한번 볼까요? 이 녀석의 그레디언트 벡터가 이렇게 된 거 그게 다 알고 있겠지? 크리티컬 포인트는 0, 원점에서밖에 안 발생하네요. 그런데 이거 해시한 생각해 보면은 200 마이너스 나와요. 이거 뭐예요? 행렬식이 음수지, 그치? 그러니까 이거는 인데피니트. 그러니까 이 녀석은 새들 포인트라는 뜻이야. 그쵸? 자, 요거 한번 볼까요? 조금 더 복잡해졌는데 사실 뭐 전반적인 이론 다 똑같아. 그레디언트가 제로가 되는 포인트를 찾았으니까 이 세 개의 포인트가 나왔어. 그런데 해시안 한번 찾아볼까요? 이 녀석을 x에 대해서 미분한 게 여기에 들어가야 되고 이 녀석을 y에 대해서 미분한 게 여기에 들어가야 되고 이 녀석을 x에 대해서 미분한 게 여기에 들어가야 되고 이 녀석을 y에 대해서 미분한 게 여기에 들어가야 돼. 그치? 여기 x랑 y의 욕 포인트 대입해 볼까요? 그러니까 y밖에 들어갈 게 없군. 0이면은 요거죠. 그쵸? 그러면은 음, 이건 뭐야? 행렬식이 음수네, 그치? 그치? 그러니까 이거는 인데피니시니까 안장점. 그러니까 요 포인트 안장점이 된다는 소리지, 그치? 그 다음에 요 포인트와 요 포인트에서는 이게 행렬식이 이렇게 나오거든요. 이게 양수고 행렬식도 양수가 나오거든요. 그러니까 요 포인트 두 들에 대해서는 파지티브 데피니니까 이건 로컬 미니멈이 되는 거예요. 자, 그런데 이 세컨드 디리버티브 테스트가 언제나 모든 케이스를 완벽하게 다 커버하느냐? 그건 절대 아니에요. 요 예제 하나 볼까요? x제곱이라는 함수가 있어. 크리티컬 포인트는 요거지, 그치? 그래서 y축에 있는 모든 포인트들은 다 크리티컬 포인트가 돼. 그치? 그런데 이건 뭐야? 행렬식이 0이죠, 그쵸? 그러니까 지금 이 세컨드 데리버티브 테스트가 되게 괜찮은 건데 하나 문제가 뭐냐면은 어디 있어? 아, 맞아. 행렬식이 제로일 경우에 대해서는 우리가 워킹할 수 없다. 그러니까 행렬식이 제로인 경우에는 우리가 좀 더 생각을 해줘야 돼. 이 경우에는 이 포인트가 로컬 미니멈이라는 겁니다. 그래서 해시안을 확인해서 해시안의 행렬식이 제로면은 다음 시간에 이렇게 할게요. 수고하셨어요.